So far with energy, we know that if you have an object, say this ball, and this ball is moving, then that ball has energy. What kind of energy? It has a kinetic energy that's equal to 1/2 times its mass times the square of its velocity. We also know if that ball was just sitting up on a table somewhere and it's above the ground, so it has a certain height, then the ball has energy in that case too. What kind of energy? It has gravitational potential energy. How much? It equals to its mass times gravitational acceleration times the height. But what happens if the ball is at a certain height and the ball is moving? So the ball's in the air and it's moving. Well, then it has both energies. It has gravitational potential from being above the surface and has kinetic energy because it's moving. We say the total energy of the object is EM, and I'll explain that in a second. So EM equals both energies, the kinetic energy from the movement, 1/2 mv squared, plus the gravitational potential energy from being above a surface. And EM, we would say, is the mechanical energy. Not mechanics like in your car, but mechanics, that word in physics means the study of motion. So it's the energy of the motion, which includes the energy because it's going at a certain velocity and energy because it's a certain distance above a surface. And so there it is. Mechanical energy is the object's kinetic plus potential energy. So let's look at a few examples. The examples aren't from your textbook, they're from a different textbook, so just follow along. We have a 0.3 kilogram baseball thrown in a straight line through the air. The baseball is at a height 2.5 meters above the surface of the earth, and we have its speed, 20 meters per second. What's the total mechanical energy of the baseball? Well, we have a formula for that. It's just the sum of kinetic plus the gravitational potential energy. 1/2 mv squared is kinetic energy. We'll add that to the potential energy, mgh. Just to draw this baseball, it's moving at a speed of 20 meters per second, and it's at a height above the ground of 2.5 meters. So that's our situation. We want the mechanical energy. I think we have enough information to fill in this equation. 1/2, the mass is 0.3 kilograms, 0.3. The speed is 20 meters per second, that will square. mgh, mass is 0.3 kilograms. G, since we're on Earth, is 9.81 meters per second squared, and the height is given to us as 2.5 meters. Anytime we're dealing with energy, we have to make sure the units we're using are appropriate, the standard units. Kilograms, meters, and meters per second, as well as meters per second squared for that gravitational acceleration. If you use all the standard units, you should get an answer in joules, which is what you want. And our final answer here should be 67.4 joules. 3 significant digits in that final answer to match the 3 significant digits in all of our data. Next example, we have a seagull flying horizontally at 8 meters per second, carrying a clam with a mass of 300 grams in its beak. Calculate the total mechanical energy of the clam, not of the seagull, of the clam, when the seagull is 30 meters above the ground. Okay, so, I don't know, here's our seagull, and let's say this little red thing is a clam in its beak. Now that red thing has a mass of 300 grams, and the seagull, and therefore the clam that it's holding, is moving at a speed of 8 meters per second. while flying at the same height that the seagull is flying, which is a height of 30 meters above the ground. So we have our equation for mechanical energy, which is what we want. 1/2 mv squared plus m times g times h. We will start plugging in our numbers. 1/2, and here, watch out. This 300 is 300 grams. We're going to need to convert that into kilograms, because kilograms is that standard unit for mass. So let's multiply by the fact that in 1 kilogram, there are 1,000 grams. Therefore, grams on top cancel with grams on the bottom. In your calculator, 300 divided by 1,000 gives you 0.3 kilograms. Okay, so your mass is 0.3 kilograms. Your speed is the same speed as a seagull, 8 meters per second, that you're squaring. Add that to a mass of, again, 0.3 kilograms. G, since we're on Earth, is 9.81 meters per second squared, and the height is given to us as 30 meters. Plugging it all into our calculator, we get 97.89 joules, but our data has 3 significant digits for all our data, so we should end up with 1, 2, 3 significant digits. Our final answer should be 97.9 joules. Okay, let's look at this next question. We have a high jump athlete leaping into the air in an attempt to clear the bar. At the top of the leap, the athlete has a total mechanical energy of 3 times 10 to the 3 joules and is moving at 8.33 meters per second. Calculate the gravitational potential energy of the athlete. Okay, so you have someone who runs and then leaps over some high jump bar. There we go. And we're told something about the energy, how fast they're moving, and the mass. And we want to figure out what the gravitational potential energy is. Okay, so we know mechanical energy is equal to 1/2 mv squared plus mgh. What are those two pieces? Mechanical energy equals the kinetic energy of the object, let's just write that as EK, plus the potential energy of the object, we'll write that as EG, gravitational potential energy. Okay, so this is mechanical energy, kinetic plus potential. All right, what we want to figure out is what the gravitational potential energy of the athlete is. So let's isolate that equation boxed in red for gravitational potential energy. So we're starting with this. We'll subtract EK from both sides. So we'll have mechanical minus kinetic energy equals gravitational potential energy. And we can break this, we can start filling in numbers here. We know the EM. We were given that, and I'll explain that in a bit. Whereas the kinetic energy, we know we can write it as 1/2 mv squared. And all that's going to equal the gravitational potential energy. Now, before we fill in the numbers, let's take a look at the question again. We're told that the athlete has a mass of 55 kilograms. It's telling us at the top of the leap, the athlete has a total mechanical energy of 3 times 10 to the 3 joules. So the mechanical energy at this point is 3 times 10 to the 3 joules. And we're also told that the athlete at this point is moving at a speed of 8.33 meters per second. So that should give us enough information to fill in for our equation here. Mechanical energy is the 3 times 10 to the 3. 3 times 10 to the 3 joules. We're going to subtract from that the kinetic energy, 1/2 times the mass, which is 55, times the speed squared, 8.33 squared. That gives us our gravitational potential energy, which is 1091.8 joules. Now, if we look at significant digits, each of our data pieces of data have 3 sig digs. So what we should do is write this as 1.09 times 10 to the 3 joules as a final answer. Now what's interesting here is, now that you have the gravitational potential energy at that high point of the jump, you can actually figure how high the athlete jumped, right? So if I take this EG number and I said, how high did the athlete jump? Well, I know that EG equals M times G times H, and we just figured out that EG equals 1.09 times 10 to the 3 joules. So I can isolate for H by dividing by mg on both sides. And then I'll have height then equals 1.09 times 10 to the 3 divided by a mass of 55 times Earth's gravitational acceleration of 9.81. And solving for that, we would get 2.02 meters. So that athlete jumped 2.02 meters high. Let's take a look at one more example. You have a construction worker. So here's a building for you, and a construction worker drops a hammer from the roof. When the hammer is 50 meters above the ground, so let's say the hammer dropped part way, and now the hammer's here at a height of 50 meters above ground. When the hammer's at that height, it has a total mechanical energy of 1.88 times 10 to the 3 joules. At that point, 50 meters above the ground, we want to calculate the kinetic energy of the hammer. Okay, so start with your mechanical energy equation. Mechanical energy equals the kinetic energy plus that gravitational potential energy. If what you want is kinetic energy, you'll have to subtract gravitational potential from both sides, and you'll end up with kinetic energy equals mechanical minus the gravitational potential. You're given the mechanical energy. You're not given the gravitational potential energy, but you're given height, you're given mass, and you know you're on Earth, so you have G. So we can break this equation down a little bit into EM minus M times G times H, and then we can fill in our numbers. Mechanical energy being 1.88 times 10 to the 3 joules. And then we're subtracting from that a mass of 2 times a G of 9.81 times a height of 50. Plugging all that in, you should be getting 899 joules of kinetic energy at that point. And once we have that kinetic energy, we could ask the question and answer, how fast was the hammer moving at that point? Well, if 899 is our kinetic energy, EK equals 899 joules, and we know that kinetic energy equals 1/2 mv squared, we can just solve for v. How do we do that? To get rid of the half, we'll have to multiply by 2. To get rid of the m, we'll have to divide by m, and then we'll have to square root all of that to get rid of the squared sign. So we're going to multiply, let me make some room here. We'll multiply by 2. We divide by the mass, which is 2 kilograms. And we'll take the square root of all that. Plugging that all in, your final answer should be to 3 sig digs, 30.0 meters per second for how fast. So no homework over the weekend for this. We'll do some problems involving mechanical energy next week when we look at the law of conservation of energy, which says the mechanical energy of an isolated system does not change. Don't worry about it. We'll cover it next week. Thanks.